and I'd like to thank the organizer as well for giving me the opportunity to speak in front of such an audience. And now that I've seen the previous presentation, I should also thank the... Oh, do I have to wear it? Oops. Ok. How do you... Come te lo metti? Cos'è? No, dietro. Ah, dentro vorrei. Okay, should I start over? Somewhere. Oh, is this a pointer? Is it supposed to be a pointer? Oh yeah, it's tiny. Sorry. Just in. It's tiny, okay. Because the previous presentation introduced some of the points that I would like to start from, actually. Sorry, the title sounds a bit fancy, Horizon Quantum Mechanics. I will try to convince you that it's just a simple idea. In fact, let me start with some motivation. The first point of my motivation is that I can't even see, can you see it? World is quantum and black hole should be quantum. When I say the world is quantum, what I mean is that our best description of the data we collect from the universe is quantum physics. I think we can agree on that. And therefore also black hole should be described by some quantum states. Of course, this opens the question, how much of classical general relativity should we retain? And I think the previous presentation touched upon this. How much of general relativity is still good when we want to describe black holes? It's an open question. The second point, whatever the quantum state that represents a black hole might be, we can agree, I suppose, that black holes are gravitational bound states, right? Nothing escaped from that, presumably, or very little. But this opens another question. How much can we learn from, let me call it scattering theory? Gravitational waves could be an example. Why scattering theory? I don't particularly want to fall into black hole. I don't know if you would volunteer for entering a black hole and see what's inside. So all the information we can collect could only come from throwing something in and see what comes out. I think we can agree on that. That's a big problem because bound states in quantum physics are usually complicated objects and not all the properties can be told from just looking what's coming outside. And now the next question, which is what I will focus mostly, is what characterizes these bound states as black holes? And from general relativity, we could say the quantity that makes the difference is the gravitational radius. For a Schwarzschild black hole, it would be the Schwarzschild radius. And so I'd like to try and quantize that observable. Nothing else than that, in order to tell whether a quantum state is a black hole or not. So, I can skip the plan of the talk. We have already been told about the Oppenheimer-Schneider model. It's the simplest example of gravitational collapse. You have a collapsing ball of dust. At some point, it crosses its own gravitational radius that becomes an event horizon. That's the simplest possibility. And then all the matter is supposed to follow into a central singularity, which is, of course, a big problem for quantum physics. Naively, you expect that if you're trying to shrink a finite amount of energy into an infinitesimal volume, quantum fluctuation will blow up and prevent you from doing that. So presumably, we could all agree there's something wrong there in this picture, but how much of the remaining picture is still correct? Here's an open question. The key role here is, again, played by this quantity, the size of the would-be horizon, which is told us by, it's called gravitational radius. What is it? Well, it's easy to introduce the gravitational radius for a spherically symmetric system. You can write the metric in this form. You choose to use the areal radius as one of your coordinates. So 4 pi small r square is the surface, the area of a sphere in your system. Then Einstein equations tell you that the GRR component of the metric has this form, where E is the Misner-Sharp mass. Basically, it's a flat space integral of the matter density that you have in your system. Now, you take that quantity, multiply times 2, times the Newton constant, and that's the gravitational radius. It represents the total energy inside the sphere. And if it so happens that small r is equal to the gravitational radius somewhere, that becomes a trapping surface. Roughly speaking, the escape velocity there is the speed of light. If the system is static, if there's no evolution, that's the horizon. Okay? So the gravitational radius plays a key role in telling us, in a classical system, whether we have trapping surfaces or horizon, therefore black holes. And I would like to quantize that quantity if I want to describe black holes in a quantum description. In this particular presentation, I will only consider the ADI mass, which is the limit of the Misner-Sharp mass when I take the small r to infinity. So basically, the ADI mass is the total energy in my spherically symmetric system, what I would see asymptotically, again, as an observer far away. But you could do better than that. Now, how do I make a quantum description of these quantities? In the simplest possible way to begin with. So I consider two observables. I call one of the observables the Hamiltonian, it's actually the ADM mass. And the other observable, I call it the gravitational radius, is what I want to describe quantum physics, quantum mechanically. Both observables have their own eigenstates, and a general state in my Hilbert space will be given by a linear combination of their outer products in that form. That's as simple. Now, the gravitational radius and the ADM mass are not independent quantities. They must be related by this relation. So I impose this constraint on the quantum states so that only the physical states that satisfy this constraint are good candidates for describing my quantum system. And the solution is very simple. It tells us simply that my physical states are sort of diagonal in the energy, Hamiltonian eigenstate and gravitational radius eigenstate. They come in fixed pairs. And the coefficient there remains undetermined. Now, if I take a physically allowed state and I trace away the gravitational degree of freedom, let me call it the gravitational radius degree of freedom, what I obtain is simply the spectral decomposition of my system, where again with energy I mean the ADM energy of the system. If I instead trace away the Hamiltonian eigenstates in this way, what I obtain is what we call the horizon wave function, which is basically another wave function that tells us the amplitude of finding the gravitational radius having a certain size. And this is again for the ADM mass. You can do a local construction, but I don't want to go into that. It's in this paper if you are interested. Example, most of the time we play this game in the reverse order. We actually start from a wave function representing a localized state, let's say a particle, localized in space, so we represent it with a Gaussian wave function with a certain width, which we assume is related to the mass by the usual Compton relation. We do the spectral decomposition. Remember, it comes into play at the end of my derivation before. Now it's intermediate step. Spectral decomposition, just a change of variable basically, and we obtain the horizon wave function. Okay, easy for Gaussian states. You can do the calculation. There's a point here in order to go from position space to energy space, momentum and then energy. I use flat space dispersion relation because I remember here the Misner-Sharp mass is obtained by integrating in a fictitious flat space. So that's analog. But if you want to play the game differently, you can choose a different Hamiltonian. That's model dependent. What do I do with this? Well, that's the question I was starting from. Is my system a black hole or not? Basically, what I can compute now is the probability density that the particle is inside its own gravitational radius. If it is inside its own gravitational radius, presumably it's a black hole. It will be given by conditional probability that the particle is found within a certain sphere of radius Rh times the probability density that Rh is the actual gravitational radius of the system. Yeah, usual quantum mechanical stuff. Now I then finally integrate on all possible value of Rh. Why? Because the question is the system a black hole or not? I don't care what its horizon is. So whatever the horizon is, if my particle is inside the gravitational radius, that's a black hole. And for example, here I can plot this quantity. The calculation can be done analytically. And what I find is the probability that my Gaussian packet is a black hole as a function of the mass, has this form, this shape. If the mass is of the order of a Planck mass, the probability is close to 1, and then saturates to 1, of course. If the mass is like, let's say, 1/3 of the Planck mass, it's already very small. We recover some sort of very intuitive result that you could obtain from very qualitative arguments. Remember, the Planck mass is the mass of a particle whose Compton length is equal to the Schwarzschild radius. And presumably, if you have a smaller mass, quantum physics prevail and you have no classical geometry. Whereas if you have a larger mass, perhaps geometry prevails. This is what this plot is telling us. So it's a sort of check that we are not doing things so crazy. And so we started applying this idea to different cases. I will only mention briefly the GUP with Fabio, who's in the audience. And then this led us to consider extended quantum states of black holes. I'll show you why. The general idea of Bose-Einstein condensates, black holes, is Diaz, who's in the audience as well. And then I will show you briefly how you can extend, starting from here, how you can extend this treatment to rotating sources, which are a lot more complicated, presumably more realistic. Okay, first, how can we recover a generalized uncertainty principle from this construction? Now we have the wave function representing the size of our source, and that comes with an uncertainty. Remember, it's a Gaussian, it has a certain width. But we also have the wave function that represents the size of the horizon with a certain uncertainty. Okay, it goes like 1/L. So we could conjecture that both uncertainties limit our ability to tell where the source is or how large the source is. And so we can combine the two uncertainties linearly with some coefficient of your choice. And what you obtain is the typical GUP behavior for the uncertainty in the size of the object versus the uncertainty in the radial momentum in this case. It has a minimum and then it starts growing again. We have obtained this result, by the way, without assuming any modification of the commutation relations. There's no change in the kinematics there. It all comes from the definition, again, of the gravitational radius and its quantum treatment. But there is a problem. Imagine you want to use this Gaussian here, to describe an astrophysical black hole with a very large mass, huge mass compared to the Planck mass. The problem is that in order to have both a very large horizon size and the large mass, which are the same, you need a very small Gaussian width. So small that the uncertainty in the horizon size as well grows the same way. So eventually, if you imagine that all the energy in your system is confined within a central singularity, smeared slightly as a sub-Planckian Gaussian, your horizon seems to fluctuate hugely. Imagine you have an astrophysical black hole, several kilometers in size. Its horizon fluctuates by several kilometers. Does it sound reasonable to you? It doesn't sound reasonable to me at all. So either the entire formalism that I've built is wrong, or maybe we should consider a different state to describe the black hole. Your choice. My choice was, okay, let's stick with it and see if we can find a different description that doesn't have this problem, and consider black holes as spatially extended states. How extended within the inner horizon? Well, that's an open question, but I think it's reasonable to assume that the quantum state cannot be there, just in the center. Okay, so I will not spend much time talking about this idea that black holes are Bose-Einstein condensate of self-sustained gravitons, because probably Gia will talk about them tomorrow, something. Anyway, the idea is that a black hole is given by a large number, and is a large number of gravitons confined in their own potential. So you can describe the state of each graviton in this very large number of them as living in a potential, mean field potential generated by remaining n-1. The condition that is kind of fancy is that they should be marginally bound. You can think in Newtonian terms of as like their energy is just at the edge. So if you push them a little bit, they escape. This condition, the marginally bound condition, is what ensures the scaling relations. The size of the horizon is equal to the Compton length of these objects. Their energy scales like 1 over square root of n. Anyway, these are details that for calculation that I'm going to be interested in are not very relevant. I only find it interesting that you can reproduce the Hawking radiation here. And simply because you estimate the probability that some of those objects are kicked out by their self-interaction, it turns out to be the same formula you obtain during the Hawking calculation. And the other funny thing is that if you emit one of these gravitons, the bottom of the potential lifts up because it's proportional to the number of gravitons you have there, so the system remains at a critical point. But again, these are details. The question we would like to ask here, is this system a black hole? Meaning, if I apply the horizon quantum mechanics analysis, do I obtain that this object has a large probability of being a black hole or not? And small fluctuation or large fluctuations in the horizon size? Well, what we did was to represent this condensate by superposing n, a large number of gravitons, each of which has a probability of being 8, that represent the true condensate, but also some small probability of being an Hawking quanta, so some of them can escape. You build the n-particle state of these gravitons, you do the spectral decomposition. Mostly the final result depends on what is their Compton length. If you assume their Compton length is indeed equal to the expectation value of the gravitational radius you compute at the end, the probability turns out to be practically 1. So these objects are good candidates for being black hole in our meaning. Imagine a number of such physical black holes, practically 0. The problem we had with the Gaussian before has disappeared. Many soft gravitons. Let's see. Oh, not all. Many soft gravitons do the game of producing presumably an astrophysical, good description of an astrophysical black hole. Now, going back to this simple model, we can also give a more detailed description of each graviton state. For example, approximating this sort of potential with an harmonic potential well. It's not so bad. If you do that, we call that the harmonic model of the quantum black hole. The reason is simply you know analytic solutions. So you know exactly how each graviton is spread in space, which is part of our requirement of computing the horizon wave function. And then you know in a spherically symmetric harmonic potential, you can have angular momentum. You are tempted to say, okay, let's try to build a spinning black hole instead of just a spherically symmetric one. Of course, it's a task. As we heard before, rotating source is complicated, and nobody has a clear description of formation of rotating black holes from matter sources. From our point of view, there's no Misner-Sharp mass for non-spherically symmetric sources. By this I mean particular the fact that there's no function from which we can easily recover the location of the trapping surfaces, which is what we need. And unfortunately, I don't think there is an easy solution for that. But we can just try to reproduce the asymptotic global analysis we did before for the ADM mass. So look at from far away and use the asymptotic Kerr charges. Let me call them Kerr charges, by which I mean the total ADM mass of the system, the angular momentum, as seen from far away. So now, instead of having just the ADM mass, corresponding quantum operator, I also have angular momentum, the corresponding quantum operator, and two candidates for the gravitational radius or the horizon system, which is the usual, given by the usual calculation. So I have 4 observers per space. I will impose 2 constraints and do some analysis. Well, what I'm going to show you in the last couple of minutes, instead of taking a certain state, a certain wave function in position space, I actually build my I want to build my black hole starting from the building blocks I showed you before. So I choose to have n gravitons. All of them are in the same state of the harmonic model. Choose, for example, n equals 0, angular momentum with graviton equal 2, and the projection along the z-axis, or vertical axis, plus or minus 2, I suppose all gravitons are either spin up or down. Reciprocate. The expectation value of the Hamiltonian must be equal to the total EDM mass of my black hole. I have the expectation value of the angular momentum. A very important quantity in this description is the Compton length, let's say, let me call it the Compton length of this graviton, this length here, underneath. I can fix. I'm building the system, so I decide what it is. Now, one thing that one to notice is that depending on this length, of course, my graviton will be either inside the expectation value, for example, the outer horizon, or not. In particular, the specific cases we consider, if this lambda mu is 1/4 of the expectation value of the outer horizon, all of the graviton, each graviton is well inside H plus. Double lambda mu, and you are in a critical situation. There's a good probability that the gravitons are either inside or outside. Make it 4 times larger, so lambda mu equal to the expectation value of the R plus, and the gravitons are mostly outside. So this is not a good candidate to build a black hole. This is a good candidate, that's borderline. Still interesting for the following reason. Consider the 2 cases that could be black holes. So for lambda mu, 1/4 of the expectation values are plus. Here are the expectation values of the 2 radii, R plus, R minus. You see, even with the maximum amount of angular momentum, the 2 radii don't meet, which means the external configuration cannot be reached. But the good thing is that the probability that the outer horizon is realized, quantum probability, according to the function that we obtain, is practically 1. I just need to have at least, let's say, 10 gravitons, order of. It's fine, this is a good model of that. This horizon has much less probability to form. I won't show you here a very good paper. So basically, it seems like quantum physics allows for this, but not for that. And it doesn't, but this single model, not what I'm drawing in, a quantum conclusion doesn't actually reach the external geometry. This choice of lambda mu, on the other hand, lets you reach the external geometry, the 2 radii meet there, actually a little bit before having all the gravitons aligned up, for example. But the probability that the outer radii, the outer radius is actually an horizon, you see, is 0.67 to the power n. So if n is large, this goes down very fast, practically 0. So with this very simple state that we build in order to describe the spinning black hole, we can obtain something that's not extremal very easily. Extremal geometry, not quite, because this is not, probability that this object turns out to be a black hole is 0, or very large number of them. Does it mean anything? I don't know. But I think the lesson here is, if you try to do quantum mechanics with black holes, there's Pandora box opening in front of you. And all experiments will tell what's right.